Well, I said that there were 3 contact forces where we know the direction of the force. So there are 3 contact forces with known directions. Those are pushing, and that pushing force is perpendicular to the surface toward the chosen body. The second one is pulling. You can always think of that as with cables. And the third one is friction. And we've done these 2, so the only one we have left is friction. So what do we know about the friction force? So first, for the direction, we know that friction force is always parallel to the surface of that it's sliding along. Second, we're going to break it up into 2 separate types of friction: kinetic friction. This is if there's already sliding happening between the 2 bodies, or already sliding of the body you're looking at relative to what it's resting on, in contact with. In that case, for kinetic friction, the direction of the friction force is always opposite the velocity, okay? So we already know it's parallel to the surface, but that can mean one of 2 directions if it's parallel to the surface, right? This tells you that along that surface, it's always going to be the opposite direction of the velocity. And if they're both moving or whatever, the 2 things that are in contact, it's opposite the relative velocity. You know, it's opposite the direction that that your chosen body is moving relative to the one it's in contact with. So and the magnitude of that force. So this is the first one of these where under certain conditions, we actually know the magnitude of that force too. The magnitude is the coefficient of friction times the pushing force applied by the contacting body, okay? So this is the pushing force applied by the contacting body. They always occur in pairs, okay? I'm acting like you haven't seen this before. You did 2 weeks of this, or I don't know how long, but you talked about this in Physics 1. But this is the pushing force applied by the contacting body. Okay, the other possibility is that it's static friction. Well, if it's static friction, we're sort of going back to statics, you know. So we're not going to see that as much in this class. But if you have static friction, that friction force is still parallel to the surface. But the direction is opposite, well, it can't be opposite the velocity because it's not moving. It's opposite the acceleration that would be occurring if there were no friction. You know, that would occur without friction. So if you can't figure it out from eyeballing it, you can do the calculation without friction, see what the direction of acceleration is, and then the friction force acts in the opposite direction, and you do the problem again. That's kind of a pain, but that's how you would have to do it. Okay. The magnitude is not quite as simple as with kinetic friction. In this case, the magnitude can be anything up to the coefficient of static friction times that pushing contact. Okay, so if you're in kinetic friction and you know the coefficient, you can actually calculate that friction force, and that has to be true. With static friction, that's not the case. It's going to be anything required to maintain static equilibrium up to this value. Okay. Okay, so let's do a simple example, and then we'll do a more complicated example. So let's say this is 5 kilograms. This is 2 kilograms. Let's say that at the instant shown, the system is moving this way, and the coefficient of kinetic friction is, let's call it 0.1. Okay. What's the acceleration vector of the 5 kilogram mass? We're going to have to do this the same way that we did before with systems, but now we're going to have to include the friction in it. So let's start by isolating the 5 kilogram. So 49.05 down, that's the weight. There's a pulling force from the cable this way, away from the body. And now we have to deal with that friction contact. There's always a pushing contact from the surface and then a friction contact. So the pushing contact from the surface is this. Is this kinetic or static friction? Yep. Kinetic, yeah, because they're moving. Also, I guess the coefficient I gave you had said it was kinetic. So if the velocity of the 5 kilogram is to the right, that friction force has to be to the left. And the value of that is 0.1 N. Okay. Newton's second law says negative 0.1 N 0 plus 0, negative 49.05 plus 0 N plus T0 is equal to, now with the accelerations, we're going to do it the same way that we did with the things on pulleys before. This acceleration, all we have to figure out is that moving along X or Y? This is accelerating along the X-axis, so A0. Notice that when we did problems with pulleys before, we only had 2 variables in our equation we wanted to save. This time we have 3, but notice that if you do the y equation first, you can figure out what that n is and plug in to the x equation. Okay, so the y equation says n is equal to 49.05. Now plug that into the x equation, and you get negative 0.1 times 49.05 plus t is equal to 5a. So I'll write this as t minus 5a is equal to 4.905. And that's my first saved equation for the system of equations. Any questions about that one? That's the body with friction on it. And so, but, you know, that's 2 variables in a single equation. So now we have to isolate the other body. Yeah, question?
When calculating friction, is it nominal force of gravity times coefficient of friction?
It is not always, because in this case, you're right that it is. But if this was on an incline, or
the gravity in the y direction, then that's friction and friction.
yeah, then I mean, like depending on the case, you just have to think about that a little. So I'm gonna bring up those angles and stuff in a second. But yeah, in this case, that's exactly what it is: the weight times. But get in the habit of just writing out that whole free body diagram and going from there. You know, be sure you figure that out, because thinking about it too simply like that can lead you astray sometimes. You know.
It can also be friction between 2 sliding objects, which wouldn't necessarily be the weight forces.
Friction between, yeah, I mean, there's just a lot of cases where, yeah, where you don't want to think about it that way. Okay, the 2 kilogram now. So we have the weight force of 19.62. The cable force, it's the same cable as on the sliding one. So the rule is parallel to the cable, away from the body. And Newton's second law says 0t plus 0, negative 19.62 is equal to 2. Now we have to think about the direction. So think about the 1 inch thing. If we move our first body an inch in its positive direction, where does the 2 kilogram go?
Down.
Down. So that's the negative y. So we're going to write this as 0, negative a. And we get this equation out that says t plus 2a is equal to 19.62. And those are our 2 equations. So we have t minus 5a is equal to 4.905. And then t, I'm going to subtract this second equation. So minus t minus 2a is equal to minus 19.62. And so you get negative 7a is equal to, what would that be? I'd have to calculate that. Can someone punch that in?
For A?
For just 4.905 minus 19.62.
Negative 14.715.
Negative 14.715. And so then A is equal to, divide that by 7.
2.102 or negative 2.0.
It's positive, right? They're both negative? Okay. 2 point, tell me the decimal again.
102.
102 meters per second squared. Now plug that into the acceleration vector for whichever one you want. I specified that we want the acceleration of the 5. So the acceleration vector of the 5 is 2.10 and then 0. So is this system speeding up or slowing down? Can you tell based on this? Speeding up because if the velocity and acceleration are in the same direction, you know, this acceleration is this way. If they're in the same direction, it's speeding up. If they're in the opposite directions, it's slowing down. Okay, so in other kinds of like pulley problems, I never asked you at the end whether the thing was speeding up or slowing down. Why is that? Like, imagine this system without friction, okay? We've done a couple of problems like that, and I've never asked you whether it's speeding up or slowing down. Is there a reason for that, or I just haven't done it? Yeah.
Because it would actually be possible for it to slow down because of the friction.
Well, so really the answer is just what I've given you going into the problem. In these kinetic friction problems, in order to know the direction of that friction force, I have to tell you the velocity, okay? So we have the direction of the velocity, and so we can answer this question. On other problems, I want you to notice, like, I never gave you the velocity before, and it wasn't just because I was like glossing over it. It's because the answer to everything we've done up to this point has been the same no matter what the velocity was at the starting point, okay? Like, when you do a problem like this, for example, okay, we calculated the acceleration without me saying anything about the velocity at this instant. Okay, that's because whether the one on the left has a downward velocity or whether it has an upward velocity, it doesn't affect any of the forces, and so it doesn't affect the acceleration. So based on the amount of information I've given you for those problems, it could be speeding up, it could be slowing down, it could be at rest at that instant and just starting to speed up. Okay, but with friction, you always have to know the direction of the velocity. Okay? All right, in physics 1, you did, I don't know how long you spent on it, probably a class or two, dealing with friction on inclined surfaces, okay? And when you did those, that's a terrible line. Oh, that's good. Okay. Remember, you always used a rotated coordinate system for this, okay? You could do it in a regular coordinate system, but it would just be, the math would just be more complicated. So you always chose a coordinate system with your y-axis pointing straight out of the surface and your x-axis along the surface in such a way that the z-axis is coming out towards you. So your z-axis is coming out of the page like that. And remember that using a coordinate system like that simplified a bunch of stuff, but it made the weight force more complicated, and so you had to use, trigonometry, think of right triangles and stuff to come up with what the weight force is in that coordinate system. Okay. I want to introduce a new way to represent stuff in this rotated coordinate system that is much quicker and easier than using right triangles once you get used to it. And it's going to come up in future classes. We've already done this in D-form, so you people have seen this stuff before. But basically, wouldn't it be nice? Wouldn't it be nice if there were just a simple function that took a vector in one coordinate system and re-expressed it in another coordinate system. There is. So these functions are, the function is multiplying by a rotation matrix. And for any coordinate system transformation, there's a rotation matrix that'll re-express every vector that you have in one in the other one. Okay? So this is rotation matrices. And so you always want to think of the rotation that's required so that the original coordinate system becomes aligned with the new coordinate system. Okay. And I'm going to give you these rotation matrices for rotations about the x-axis, the y-axis, and the z-axis. What you call a positive angle about those axes is determined by the right-hand rule. So remember the right-hand rule. You want to use the right-hand rule with your thumb in the axis direction. Okay, so if you're rotating about the x-axis, so how am I going to represent this? Let's say well, let me just draw it with the x-axis coming out towards us and the y-axis up and the z-axis this way. So what would a positive rotation about the x-axis look like? If you rotate positive theta degrees about the x-axis, your x-axis would still be facing straight out. But your y-axis would be that way, and your z-axis would be that way. This angle is theta, and this angle is theta. Okay? And the rotation matrix is 1, 0, 0, 0, cosine of theta, sine theta, 0, negative sine theta, cosine of theta. So that's the matrix, that's the rotation matrix for transforming the coordinate system about the x-axis. Remember that so this can be confusing because you can also rotate vectors around axes. You can imagine just reorienting a vector about an axis. And that matrix looks like the inverse of this. And so in this class, whenever I do coordinate system, whenever I'm dealing with rotations of any kind, I'm doing it using this rotation matrix representing a rotation of the coordinate system, not a rotation of the vector, okay? So like in later engineering classes, if you ever see a rotation about the x-axis that looks like cosine theta, negative sine, positive sine, cosine, that's a rotation of the vector, not the coordinate system, okay? Which if you think about it, a rotation of the vector around an axis is really exactly the same thing as a rotation of the coordinate system in the opposite direction. Okay? That's okay, so that's the rotation matrix about the x-axis. Now about the y-axis. So let's think of looking up from above. So there's the y-axis. Here's the x-axis. Here's the z-axis. And say we're going to rotate an angle of positive theta about the y-axis. This rotation has to go along with the right-hand rule, so put your thumb in the direction of the y-axis. A positive rotation would put the x-axis that way, and the z-axis this way. And that rotation matrix is cosine of theta, 0, negative sine of theta, 0, 1, 0, positive sine of theta, 0, cosine of theta. These are pretty easy to program into your calculators. So let me know if you want help doing that. In this class, we're probably not going to do enough that you need to do that, you know, but it's a nice thing to have. When you see how quick and easy this works, once you're familiar with it, instead of thinking of like the way you did in Physics 1 for inclined surfaces, you might be drawn to just putting this in your calculator. So let me know. And then the last one is a rotation about z. So in this case, your z-axis is that way, your x is this way, y is this way. And you want to rotate theta about the z-axis. So put your thumb in the direction of z, coming out of the page. Your fingers curl in the direction of a positive rotation. So your new x-axis is going to be that way. Your new y-axis is going to be that way. And the rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. So one thing to notice about these, it follows kind of like a pattern. So identify the axis that you're rotating about, okay? And that row and column are just going to be a 1 in the spot that you're rotating about. This is a rotation about the x-axis. So we have a 1 in the x, diagonal position, and then 0, 0, 0, 0. Okay. And then for the other, there's 4 spots left because there's 9 spots in this matrix. And for x and z, they go cosine, sine, negative sine, cosine, in that order in those 4 spots. Y switches which one of the signs is negative. But other than that, it's a pattern that you can identify. Okay, so let's look at it for x. So that's, the 1s and 0s along the x row and x column. And then cosine, sine, negative sine, cosine. Now let's look at the y. In the row, the second row in the second column, the y column in the y row, we have the 1 and the 0s. And then the other 4, remember that y is the one where the signs are switched on the plus minus sign is switched on the sine functions. So you got cosine, negative sine, sine, cosine. And then z, it's back to the way it was before. The 1s and 0s in the z row and z column. And then cosine, sine, negative sine, cosine. Once you have your rotation matrix, you can re-express any vector in the original coordinate system so any vector in the original coordinate system in the new coordinate system, by just multiplying the rotation matrix times the vector. I'm not going to go through like matrix calculations and stuff, but your calculator will do this just with the regular times function. Okay, so if you set up this matrix and just plug it into your calculator, it'll do this for you. Okay, so let's see an example first with this rotation matrix. So let's say that your original coordinate system is this. That means Z is coming out. And your rotated coordinate system is this. Where this angle is 30 degrees. And in the original coordinate system, the weight force is let's say 0, negative 98.1. That would be like a 10 kilogram mass. Re-express this weight in the new coordinate system. Okay, well, what axis is this rotation of the coordinate system about? Yeah, right. And what about the direction? Is that a positive 30-degree rotation of the coordinate system about Z or a negative? Positive. Okay, so our theta is positive 30 degrees. That means that our rotation matrix is cosine of 30. Well, let me write that out first. So cosine of 30, sine of 30, 0, negative sine of 30, cosine of 30, 0, 0, 0, 1. So that's 0.866. 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1. And so now our weight force vector in the new coordinate system, all right, it is mg new, is 0.866, 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1, times our weight force vector in the original coordinate system. That's 0, negative 98.1, and then 0 for Z. And you get negative 49.05, negative 84 point, I don't remember. What's 98.1 times 0.866.
$84.95.
84.95, and then 0 for Z. And that's it without thinking about the right triangle and doing the, thinking through the trigonometry. Just multiplying by that matrix does all the transformations for you. Okay. Okay, so let's say we have an incline of 20 degrees. Well, let's do it the other way. So let's say we have an incline of 20 degrees and a mass of 5 kilograms. And a cable over a pulley connects the 5 kilogram mass to a 2 kilogram mass. And at the instant shown, let's say that the 5 kilogram mass is moving down the ramp, so that's the direction this system is moving. And the coefficient of kinetic friction is 0.1 again. We want to calculate the acceleration vector for the 5 kilogram. Okay. So we're going to choose one of these as the first body and one as the second. I guess I'll do the one on the incline first, but it doesn't matter which order you use. So a free body diagram of the 5 kilogram. We have a weight force of 49.05. We have a pulling force from the cable. This way. And now we have to deal with the friction. There's a pushing force that's perpendicular to the surface toward the body. I'll call that N. And now the friction force is opposite of the velocity vector of this body. And so that's going to be up the ramp this time. And that's equal to 0.1 N. Notice that all of these force vectors are easy to represent in this coordinate system, except the weight force vector, right? The weight force vector, so mg, is 0, negative 49.05 in a coordinate system like this, right? So we can think of that as our original coordinate system. And now we just have to think about what rotation matrix we need to transform from this into the red coordinate system. Okay, so if we're going from this to this. So first, what axis are we rotating around? Yeah, if you're staying in the plane, you're always rotating about Z. And is it a positive or a negative rotation? Negative in this case, and then what's the angle? Yep, negative 20 degrees is our, okay. So mg in the new coordinate system is cosine of negative 20 degrees, 0.940. Sine of negative 20 degrees is negative 0.342. 0. Then negative sine of negative 20 degrees is positive 0.342. Cosine of negative 20 is 0.940. And then 0, 0, 1. And just multiply that in your calculator by 0, negative 49.05, 0. And you get, what's 0.342 times 49.05? I am not getting my calculator.
You said 0.34?
Yeah.
16.775. I didn't figure out the sign.
Yeah, okay, this one's positive. 16 point what?
775 to 78.
Okay. And then what's 0.940 times 49.05?
46.107.
0.11, let's call it. And then 0. And so there is your weight force vector in the new coordinate system. Okay? It doesn't feel like much of an improvement. It feels like more work at first, you know? But once you're used to doing this, especially if you have a function in your calculator where you can just punch in the, like say the axis and the angle, and it'll just pop that out for you. It's so quick and easy. Okay, so Newton's second law now says that t is in our negative x direction. N is in our positive y direction. The friction force is in our negative x direction. What else do we have? 1, 2, and then the weight force, 16.78, negative 46.11 is equal to the mass times, and again, we don't, whichever body you choose first, you don't have to think about whether it's going to accelerate positive or negative. You just have to think x or y. So in this case, this is going to be A0. The signs will work out on their own. The y equation says n is equal to 46.11. So the x equation says negative t minus 0.1 times 46.11 plus 16.78 is equal to 5a. So negative t minus 5a is equal to 16 points. Okay, I'll get my. So 16.78 minus 4.61. Okay, so this stuff is equal to negative 12.17. And that's our first equation that we'll save. Anybody have any questions about that one? That first body? And now we'll go to the second one, the hanging mass. That has a downward force of 19.62, an upward force of T. This one, you might ask yourself, like, do I have to, in a situation like this, do I have to represent everything in the same coordinate system? The answer is you don't. You can use whatever coordinate system you want for either one of the bodies. So I'm going to use just a regular coordinate system for this one. And if you want to make sense out of why that is, remember that systems of equations are just saying, you're just listing out a bunch of mathematical facts that you know are true. And then you're solving them all together. This stuff that we got in this coordinate system here, we know it's true, okay? We're going to get a bunch of other stuff in another coordinate system, mathematical relationships that we know are true. And then those give us our system, okay? So Newton's second law says 0t plus 0 negative 19.62 is equal to 2 times. Now you have to think about the relationship. If this 5 moves an inch in its positive direction, where does the 2 go? Don't get this wrong. This one, it goes opposite of what it did last time because I have them flipped. So in this case, if the 5 goes in the positive x, notice the 2 goes in the positive y. So this time, right, we're going to write it as 0a, okay? So this is 0a. So it all comes from just thinking of those 1 inch motions. Our second equation here says t minus 2a is equal to 19.62. Now solve this system. So negative t minus 5a is equal to negative 12.17. The second one says t minus 2a is equal to 19.62. I'll just add those two and I get negative 7a is equal to positive 7.45. And so A is equal to 1.06 meters per second squared. And so the acceleration vector of the 5 kilogram is 1.060. Or down the ramp.
Quick question.
Yeah.
If there was a part B that asked for an acceleration of body 2.
Yeah.
What would we have to do to solve?
Yeah, just you have this variable A. You already know that this is the acceleration vector. It's not very complete because you didn't know what A was yet, you know. Now you know what A is, so just plug it in. And so it would be 0, positive 1.06. So the hanging one would be accelerating up, and the sliding one would be accelerating down the ramp. So yeah, just remember, you've already told everybody what A5 and A2 are. People just aren't very satisfied yet because you didn't tell them what A was. Once you calculate that, you have them both. Yes? It was not. That's why. Thank you. That's, okay, so it's not accelerating down the ramp, it's accelerating up the ramp, which means that, okay, so what's it doing? It means slowing down because the velocity is down the ramp. Yeah. Okay, that's all.